A has a linear term and has a quadratic term in the field. So therefore, A's got to be nonlinear. Okay? And then homogeneous, a material is inhomogeneous if chi is a function of position, as opposed to just being a scalar.
Which is not.
Yeah, so, yeah, does that happen on any of these? Yeah,
Sorry,
E.
on
Mhm.
Yeah.
Yeah, E. T, no. I mean, D, no, but E, yeah. Okay, dispersive, that can only happen if chi is a function of time. And so the only one of these here that that works out for is D. And then anisotropic only happens if chi is a matrix, as opposed to a scalar. So basically, scalar constant means linear, homogeneous, non-dispersive, isotropic. If it's a function of the field, and of course, if this is, I don't know, A times this plus B times this thing squared, whatever, some vector, whatever, then you could always consolidate that as C, which is a function of this guy, times the electric field vector. I mean, you could always write it that way. You could come up with a function of field for it in that way. So that's how you go through and figure out what the properties are of a material if you're given the relationship between the electric polarization and the electric field. All right. Okay, thanks, Farah. Okay, let's turn on the projector there. Is it plugged in?
It's plugged in. Try not to bump it.
And it's thinking, so that's good. Okay. Okay, well that's warming up. So, what did we do last time?
Coherence.
Coherence. And what did we learn?
Spatial and temporal coherence. That it's function.
And so, so what is coherence?
You have temporal coherence and a spatial coherence. Coherence is how much we copy a signal, then shift it in time, or maybe in different places, and then check how many they are related.
Right. See what the correlation is. Yeah, so we can think of the coherence as basically the autocorrelation of the field. Okay. And why is coherence important? Did we talk about that? Not really.
Makes sense.
Yeah, when we do interference, coherence is crucial. Okay, and we idealized spatial coherence and temporal coherence. So what's the rule of thumb for temporal coherence?
It's 1 over the bandwidth.
So, and what is 1 over the bandwidth?
Degree of temporal
Yeah, temporal coherence.
coherence.
Tau, and what's tau? Yeah, the coherence time. And what does coherence time mean?
Means if we shift the wave less than or equal than that, then the new version of the signal is pretty coherent with that.
That is right. So tau and the temporal coherence does this with the width, tau c. So if we take our field, copy it, shift it in time by, something that's less than this, then it will still be kind of coherent. If we shift it in time much less than that, then we're up here, then yeah, it's really coherent. If we shift it in time by something a lot longer than that, then we're out over here, then it's really not coherent at all.
What's that symbol at the top again?
Gamma.
Gamma. And
So-
what is that?
So gamma is the complex degree of coherence. It's the normalized version of the, what?
Mutual coherence.
Mutual coherence. So temporal coherence is the complex degree of coherence evaluated at the same position, so 1, 1, with the shift tau. And then we take the magnitude of it, and then it's just the coherence. And because it's 1, 1, then it's temporal coherence. By definition, that is what temporal coherence is. Okay, and so what that means is take a field, copy it, shift it by tau, compare it. Are they still well correlated? If they are, then we're coherent. If they're not, then we're not coherent. How much shift can we handle? Well, tau c. That gives us a benchmark. And tau c goes as 1 over the spectral width. So the broader the spectral width, the smaller tau c, the shorter the shift we can undergo and still be coherent. Okay? Now what about spatial coherence? What's our rule of thumb?
We will see how much maybe we are far from the source.
Right, so we have some source. And what we want to know is how big, rho c, of an area we have spatial coherence over. And we can estimate rho c as what?
Lambda squared divided by angular size of the source.
So lambda over the angular size of the source. So this is the delta theta. Okay. If we wanted to estimate this area, what do we call it? AC? If we wanted to estimate the area, then what did we say that was? Yeah, it'd be that squared, which we could write as lambda squared over d omega source, where this is the solid angle subtended by the source as observed from that point, that patch. Yeah.
So I'm having a little hard remembering spatial coherence, but last time we spoke about an incoherent source radiating, and so we want to know at PC what happens if all those incoherent sources are in phase or what?
So we have a bunch of incoherent point sources, so they're radiating at the same, possibly at the same frequency, but with random phase relative to each other.
Okay.
So that means if we took the field generated by one of those sources and the field generated by the other, I mean, the phase is just random.
Mm-hmm.
And then we add up a whole bunch of those, and it's just a random mishmash.
And then we want to know what at PC if the
We want to know if we took the field here, and we took the field here, and we compared them, are they correlated?
Oh, okay.
And over some region, they will be correlated, some small region. And so the question is, how big is that region? In one dimension, we can estimate it this way. In 2 dimensions, we can estimate it that way.
Thank you.
Yeah, fair.
I didn't understand the difference between theta sub s and d omega.
So d omega is just the area, so dA source over the square of this separation. So it's it's the typical definition for the solid angle subtended by something that's kind of far away, so small angle approximations are valid.
But the theta sub s is exactly the angle,
And theta sub s, we call that theta sub s. Then just in one dimension, how much angle does the source subtend? That's
all right.
Jace, you want to shut that door back there for us? Thank you.
Real quickly, what do you mean by subtend? That's not something.
That
I'm familiar
means,
with.
like, if you were to look at the sun, of course, don't look at the sun, but if you were to look at it, how big is it in angle from where
Okay.
you're standing?
Okay. That makes more sense.
Yeah. Okay. All right, so are we good with coherence? You feel ready to tackle some homework on it? So I think the next homework, I forgot exactly what it covers, and I didn't have a chance to look at it before class, but if it's just coherent stuff, let's make it due in 1 week. If it's more than coherent stuff, then maybe we'll revisit that. Okay, so what we want to do now is go to our next topic. And we can preface this by saying that the practice of optics almost always comes down to one of several things. We're either trying to control the irradiance, or we're trying to control spectrum. And in terms of controlling irradiance, it could be that we're trying to control the spatial distribution of the irradiance, in which case we're probably doing imaging or maybe displays, that kind of thing. Or it could be we're trying to control the temporal distribution of the irradiance, so the irradiance in time. And if we're doing that, then we're probably doing communications, maybe we're doing telecom, something like that. When we're trying to control the spectrum, we're basically looking at controlling the frequency content of light. And that frequency content, maybe we're doing that for the purpose of analyzing materials. Maybe we're doing it for, again, communications. So by controlling frequency, we can communicate. Maybe we're doing it in order to interact with the human visual system. So we're trying to control colors and what the human eye perceives. But usually, those are the kinds of things we're trying to control when we're doing optics. And then the question is, how do we control them? What is it that we manipulate? And generally it comes down to one of several things. In many, many devices, it comes down to manipulating the relative phase of, let's just say, of light. And usually that means we have more than one beam, and we're controlling the relative phases. And so that gets back to interference, which we'll talk about in not too long in the semester. Or we're trying to manipulate the polarization of light. And when we're manipulating polarization, we're going to talk about that. There's all kinds of things that we can do with that manipulation. Or sometimes what we're trying to do is manipulate the coherence of the light. We'll see how much time we have in the semester, but I'm going to give you some examples of that. Or we're trying to manipulate the absorption of a material or materials, and thereby control some aspect of light. usually spectrum or frequency content. So just in general, in optics, those are the types of things we tend to do. And what we want to focus on now for the next several lectures is polarization. And polarization is just crucial in terms of its importance for practical devices. So we need to become expert at it. And maybe you already feel pretty expert, in which case, great. We'll learn some fun things you can do. Maybe you feel just sort of like you're on shaky ground. That's fine. We'll fix you up. You'll become an expert. And maybe you feel like you're a zero when it comes to polarization. Totally fine. We're going to make you an expert. Because it's really important to understand and to be able to use it. And it's not that bad once you get the hang of it. But you could say that about anything, right? It's not that bad when you get the hang of it. So our job is to help you get the hang of it. So what we're going to do is let's define polarization, try to get a sense of what it is. I'll show you a visualization which hopefully gives you a better idea of what it is. And then we need to dive into the math. And in diving into the math, that's going to prepare us to be able to use polarization for a lot of practical applications. Now, in diving into the math, we're going to cover a zillion different ways of how you can represent polarization. There's a bunch of them. And it's useful to know what those are and how they interrelate because different fields tend to use different representations. So if we're going to be expert, we need to know those representations and how to wend our way between them. Okay, so definition. So we're going to define polarization in the following way. So polarization is determined by the temporal trajectory of the electric field vector and generally this is going to be in a plane orthogonal to the direction of direction of propagation. So when I should say wave vector, that's just direction of propagation. Okay, so what does that mean? Well, if we have some electric field, so notice this is the real electric field, and let's say that it's a plane wave, and let's say it's propagating in the z direction. So it's propagating in the z direction. We know, based upon what we've done already, the electric field is orthogonal to the direction of propagation. Therefore, the electric field will only have x and y components. So, if we pick some position r and freeze time, then that means our electric field is just going to be pointing somewhere. So this is some position r naught time t naught. Okay, now our definition of polarization says that it has to do with the temporal trajectory of that electric field vector in a plane orthogonal to the direction of propagation. So in other words, if we stay in this plane and unfreeze time and let it just incrementally move forward, this electric field vector in general is going to move somehow. So let's say that it moves over here. So this is equals 2. And then we let it incrementally move again and moves over here, say. So this is t is t2. We can then trace out the tip of the electric field vector, and it will follow some path. And then it will just repeat around and around that path. That's what we call the polarization, is what shape is that path. So that tells us what the electric field vector is doing in time as it propagates through this plane. And what we're going to see is that in general, that path is elliptical. But there are two degenerate cases of an ellipse. One is a line, namely this ellipse collapses down to a line. So the electric field vector is just oscillating up and down the line. So we call that linear polarization. The other degenerate case is circular, where the ellipse is circular. So the electric field vector just goes around and around a circle as it comes through that plane. So those are the two degenerate cases, but in general, polarization is elliptical, so the electric field vector traces out an ellipse as it propagates through that plane. Yeah.
So when people say nonlinear polarization, they mean either circular or elliptical?
When they say what?
Nonlinear polarization?
I've never heard of nonlinear polarization.
Really?
No such thing. Star Trek. Yeah, well, there's a lot of no such things as Star Trek. Yeah, so, yeah, it doesn't make sense.
So does, I guess light naturally is typically elliptically polarized? Is there like organic cases of like linear and circular in the universe, or is that like a man-made?
There are. And also I should tell you, just to muddy the water slightly, we're talking about fully polarized light. Later, we're going to talk about, once we understand the fully polarized case, then we're going to back off and see that you can have partially polarized light, you can have unpolarized light. And once we understand the polarization stuff, then we can define exactly what we mean by partially polarized and unpolarized. We'll see exactly what those are. We'll see how you represent them. And knowing all of that, then we can understand what's going on in any of those cases. So, yeah. What we're going to find is that fully polarized light is a property of coherent light. But it's going to take us a little while to get there. So just be aware that we're looking at fully polarized light. Okay. So, we have some vague notion that polarization is described by the shape that the electric field vector traces out as it propagates through a plane that's orthogonal to its direction of propagation. Okay, so let's take a look at what's really happening. And let's see, where is the light control? Is it only in the back jack? Yeah, if we could turn off some of the lights, front lights, yeah, perfect. Okay, so, yes. Okay, so what I want you to see or notice here is this is the x-axis, this is the y-axis, this is the z-axis, and what we have is a plane wave propagating in the z direction. And what we're looking at is, in red, the electric field. So that electric field is just propagating in the z direction. And then in this xy plane, this white bar is basically the electric field in the xy plane as a function of time. And you can see it's tracing out a line. Therefore, we are looking at linear polarization. Okay? So, that linear polarization, it could be at some angle relative to the x-axis. could be along the y-axis, could be at 45 degrees, could be at 18 degrees, whatever. But you see that linearly polarized light is just the electric field oscillating up and down and traces out a line as it goes through the xy plane. Okay, so let's keep that in mind. Let's maybe set this over here at 45 degrees. Okay, and then we could always take this and rotate it, and we could look at it head on. We can see the linear excursion of the electric field vector. Now, light does not have to be polarized in a line. We just said in general it's an ellipse. So if I take this other slider here, and we'll understand what these sliders mean in just a few minutes. Notice what's happening here. Yeah, here's an ellipse. Here we're getting to a circle, or nearly circle. And look at what it is. I mean, it's just, now the electric field is this corkscrew thing in space. And so as it propagates through the xy plane, it looks like the corkscrew shape is such that it's tracing out a circle in the xy plane. On the other hand, if I change this, here, well, the corkscrew is kind of squished in one dimension, right? And then if I take this guy, this is basically rotating the angle around which that corkscrew is rotating. So you see how that works? Okay. And then depending upon what this is, we could have this thing rotating clockwise as the electric field comes through the plane. We could have it rotating counterclockwise as it comes through the plane. But this is really the picture you should have in your head when you think of polarization. It's just the electric field vector as it propagates through space. It's tracing out some kind of a corkscrew pattern. That corkscrew could be really elliptical, could be circular, could be linear, whatever. But it's always this corkscrew pattern. Okay. So that's the picture that you should translate this two-dimensional thing into the new one. Is that. Okay, and that is polarization. It's tracking what sort of corkscrew pattern the light is tracing out. And it's doing it by just looking in a plane, so it's easy to think about and visualize. But in reality, it's going on a 3D. And it turns out that the tools we're going to develop make it really easy to understand this. To understand what's going on and how to manipulate it, and how to represent it. Okay, any questions? Yeah.
So this doesn't just apply to light, it applies to any electromagnetic field, right?
Mm-hmm. Any propagating free space field. And we chose here to show the electric field vector. But if there's an electric field vector, there's always an orthogonal magnetic field vector.
I guess I'm trying to reconcile how this is like a plane wave then. Is this just, is this like infinitely many plane waves then, or?
So this is a single plane wave.
Okay.
And a plane wave, we talked about it before in the sense that the wavefronts are planar surfaces separated by a wavelength. And so we could look at it alternatively in terms of the wavefronts, but the wavefronts don't carry polarization information.
Oh, okay.
It's just surfaces of constant phase.
Okay, that's I guess that's what's confusing me. Okay.
Yeah. And so those surfaces of constant phase, they would be orthogonal to the direction of propagation, so orthogonal to the z direction, and they'd just be stacked up, separated by a wavelength, and they'd all just be propagating together.
Okay, but they themselves don't carry any of the polarization.
Correct.
Okay, so
Yeah.
So
would this look different than this illustration if we weren't using a plane wave assumption? If we were closer to the source and it was more of a spherical wave, would this illustration even make sense?
So what we'd have to do then is pick a point in space, pick a plane at that point that's orthogonal to the direction of the light propagation at that point.
And it wouldn't be a flat plane if we didn't use the plane wave assumption. It would be.
Well, so at any given point, we could define the tangent surface, and that would be this plane.
Oh, okay.
Yeah. So it's still the same thing going on. It's just that, you know, if we've got a spherical wave coming out, then if we look at the polarization over here, we're going to pick this plane. But if we look at over here, we're going to pick this plane. But it'll be the same picture of what's coming through. Okay, any other questions? Okay. Then let's go ahead and turn the light back on.
You mentioned a little caveat that has to be like a free space wave. Does the material destroy the polarization, alter the polarization?
No, so free space meaning, okay, so let's say this. A material that is linear, isotropic, homogeneous, and, what was that? Non-dispersive, yes. Any material that has those properties, that's what the polarization will look like. And the only time it's different really is when we get into anisotropic materials, and we're going to cover that in this class. We'll see how it works. Okay. All right, we can kill that guy. Okay, so some other things to be aware of are that many phenomena, optical phenomena, are dependent upon polarization. So anytime you have reflection or refraction, that's polarization dependent. It'll be different depending upon what the polarization state is. If you have scattering from a surface, that's polarization dependent. Propagation through a material, if it's anisotropic material, that's polarization dependent. If you have a material called a dichroic material, then the absorption is dependent upon polarization state. That's pretty wild, but all of you own, or likely own, some dichroic material. And that is anytime you put polarized sunglasses on your face, those polarizers are just a dichroic material. They absorb one polarization, one linear state, and they pass the other one. So, easy, cheap way to make a polarizer. So there are lots of phenomena then that are polarization dependent, and we'll get an idea of some of those as we go through this material in this part of the semester. Okay, so now what we want to do is lay out our assumptions and develop how we're going to describe polarization. Okay, so we're going to assume that we describe everything in terms of the electric field vector. We could do the same thing for the magnetic field vector, the electric flux density, magnetic flux density, and everything would work out the same. But the reason why we choose the electric field vector, or alternatively we could choose the electric displacement, the reason why we choose those is because they tend to interact with matter much more strongly than magnetic fields do. So therefore it just is more convenient to use those representations. So we'll just choose electric field, and then we're going to be concerned about the complex representation of the electric field. And we're going to assume, actually let's do this. We're going to assume plane waves, and moreover, if we're talking about plane waves, then by definition, that's a monochromatic wave, right? Okay. So we're also going to assume that we have propagation in the z direction. Now you could say, well, gee, isn't that pretty restricted, propagation in the z direction? And my response to that is, well, if we've got a plane wave, we know it's propagating in the direction of the wave vector. Our coordinate system is totally arbitrary. So we could always just rotate a coordinate system so that the z-axis is in the direction of the wave vector. So we really don't lose anything by making that assumption. Okay, then, if that's the case, then the wave vector is just the wave number times z hat. And therefore, the e to the minus j k dot r is e to the minus j kz. So, we can write that the electric field complex amplitude is just some constant complex vector times e to the minus j kz. So that's the complex amplitude vector of our plane wave. And that's x, y, and z. Then, because the propagation is z direction, this constant complex vector is confined to the xy plane. And therefore the complex amplitude vector is also confined to the xy plane. So it only has x and y components, in other words. So we could say then that the real representation is going to be have an x component. And by the way, r here, really, it only depends on z, because there's only a z here. So x hat plus y, ey, function of z and t, y hat. So why is this only a function of z instead of the more general r? Yeah, propagating in the z direction. So the full complex representation of the wave is going to be E naught e to the j omega t minus kz. And clearly there's only z dependence here. So let's just make that explicit by replacing the r vector with z. And then we take the real part of this, and then we have the real electric field. And either way, E naught or this form is confined to the xy plane. Okay, so let's write down our real electric field in the following way. Let's say it's the real part of some constant complex vector A times e to the j omega t minus kz. And here, it's a constant vector, it's complex, and it only has x and y components. And just a moment ago, we were calling it E naught. It's the same thing. So why the heck did I just change notation? Yeah, we're just going to change notation. For now, at least. Okay, so I can write that constant complex vector in the following way. It will have a magnitude in the x direction. It's complex, therefore it also in general will have a phase. And the y component, likewise, in general, is complex, therefore it has a magnitude and a phase. And so that then is constant complex vector A. And we define or restrict these magnitudes to be greater than or equal to 0 because they're magnitudes. You never have a negative magnitude. If we allowed them to be less than 0, then we'd have ambiguities in the phase. And we don't want that. So we just say they've got to be greater than or equal to 0. So I could write the x component then as ax cosine omega t minus kz plus delta x, and the y component ay cosine omega t minus kz plus delta y. And how did I get that?
We're taking the real part.
Yeah, just by taking the real part of this thing. Okay, so in general, we could write the real x and y components this way. Or what we could do is we could shift our coordinate system to zero out this phase. And if we do that, then we would write dx as ax cosine omega t plus, or rather minus, kz, and ey to be ay cosine omega t minus kz plus delta, and delta we define as delta y minus delta x. So it's the phase difference between the y component and the x component. So in general, it makes our lives a little bit easier if we shift the origin to zero out the phase on the x component, put all the phase difference on the y component. We don't have to, but often it's helpful. And then what we do is restrict delta so that it's greater than minus pi, less than or equal to pi. So that means it's always unambiguous if we restrict it to be in that range. Okay, now at this point, we could do some algebra. I think I have you do it in the homework. But we could take these two things and square them, add them, apply a bunch of trig identities, and ultimately eliminate omega t minus kz. And if we do that, what we end up with is that ex over ax, quantity squared, plus ey over ay, quantity squared, minus 2 times cosine of delta ax ay times ex ey is equal to sine squared of delta. Yeah.
So how did you say we got there? We took those two components?
We took those two, we square them, add them together, mess around algebraically and trigonometrically to eliminate these. Turns out you can, and you end up with that.
Okay.
And you ask yourself, why? Why the heck would we want to do that? And the reason is we look at that and we say, oh, that's just an equation for an ellipse in the plane spanned by ex and y.
And it's no longer dependent on the frequency, right?
Yeah, frequency or time. And basically, that is the equation for the shape, for the polarization. And so, so this is the equation for an ellipse. And depending upon the values of ax, ay, and delta, that ellipse could be a line, it could be a circle, could be rotating clockwise, could be counterclockwise, depending upon, I mean, if we go back over to the time dependent part. And so, basically then, by specifying these three things, we have completely specified the ellipse. If we've completely specified the ellipse, we've completely specified the polarization. So this is what we call the field representation of polarization. And notice what the meaning is of these things. AX, AY, just the magnitudes of the X and Y components of the field. Delta, the relative phase of the Y component relative to the X component. That's it. Those three pieces of information fully specify a polarization state. Okay, so we could draw the ellipse or an ellipse represented by this and draw it like that. And we look at it and we say, yeah, that's an ellipse, and it looks like the semi-major axis is rotated by an angle phi relative to the x-axis. 1/2 the semi-major axis here we could call A. 1/2 the semi-minor axis we could call B. We could call the semi-major axis x prime, semi-minor axis y prime. We could do a coordinate rotation from x, y to x prime, y prime by rotating by an angle phi. And if we did that rotation, that would transform this equation into an x component in the x prime axis over a quantity squared plus a electric field in the y prime axis component over b quantity squared is equal to 1. So if we rotate to the semi-major and semi-minor axes, then our equation for the ellipse becomes greatly simplified and looks just like an unrotated equation for an ellipse. So, notice, looking at this case here, then if I could specify...
Excuse me.
Mm-hmm.
I didn't understand. When you rotate it, then is this equation?
Mm-hmm. Yeah, this equation will transform into this equation where this is now the electric field in the x prime direction
Oh, that's it.
instead of the x direction.
Okay.
And this is the electric field in the y prime direction. Yeah, that's crucial. Yeah. Okay, and so to get there, if we can specify that rotation angle phi, and if we can specify the ratio of b over a, which we just call the ellipticity, and then if we specify the sense of rotation, when we go back to this, are we going clockwise or counterclockwise around the ellipse? Then if we specify those three things, we've specified the polarization state. And usually what we do is we take the sense of rotation and we just have that be the sign of the ellipticity. So, get rid of this, make it the sign. So in this ellipse representation of a polarization state, we just have to specify orientation angle of the ellipse and the ellipticity. And that fully specifies the polarization state. And so one question is, if we have the field representation, can we get to the ellipse representation? And the answer is yes. I mean, the transform is well known to go from this form to that form. And so we won't derive it or anything. We'll just write it down. And basically, what we have is tangent of 2 times the rotation angle or orientation angle is equal to 2ax ay over ax squared minus ay squared times cosine of delta. And then this orientation angle phi is in the range from 0 to pi. So clearly if we have ax, ay, and delta, it's really easy to calculate what the orientation angle or rotation angle of the ellipse is. And so then we just need semi-major, semi-minor axes, and we can come up with those, and I'm just going to write them down. So A is equal to ax squared cosine squared phi plus ay squared times sine squared of phi plus 2 times ax ay times cosine of phi sine of phi times cosine of delta. And B is equal to the same first term plus the same second term minus the same third term. So bottom line is we can easily go from the field representation to the ellipse representation. And the ellipticity, then the magnitude of it is going to be between 0 and 1. And when the ellipticity is 0, then notice that's just saying B is 0. B is 0. Yep, line, so that's linear polarization. Likewise, if magnitude is 1, circular polarization. And so anything in between 0 and 1 is going to be elliptical. And then if delta is less than 0, then what we have is clockwise rotation, and delta greater than 0, clockwise rotation, defined as when the beam is propagating towards you, not away. It's propagating towards you. It's propagating towards you, and delta is less than 0, then the rotation you're going to see is counterclockwise. On the other hand, if delta is 0, or greater than 0, the rotation is going to be clockwise. So
delta less than 0 would be right hand?
So delta less than 0, if we want to call it right hand, left hand, then thumb in the direction of the right hand in the direction of propagation, fingers curling in the direction of rotation, which is going to be counterclockwise, right? Then yeah, that's right-handed. So you'll sometimes see this called right-handed and that left-handed for our convention of it propagating towards us. Some books will define it propagating away and then it flips, which is really annoying. So I just translate everything into towards me and then I follow that. And then I never get confused. Okay. So this corresponds to delta zeta, the ellipticity greater than 0. This corresponds to the ellipticity less than 0. So notice the sign of the ellipticity is opposite the sign of delta. Just because. I mean, that's, in order for everything to be self-consistent, that's what we have to do. Just slightly annoying, but you just get used to it. Now, alternatively, we could do the following. We could define an ellipticity angle, call it theta. And the ellipticity angle theta, we can say that the ellipticity is equal to the tangent of that ellipticity angle theta. And so if we look at what the ellipticity is in terms of B and A, then all this is saying is that we can construct a triangle with the horizontal length being A, vertical length being B, and then that angle is theta. So that's the geometric interpretation of the ellipticity angle. So if we took this and drew a rectangle that enclosed it and only touches, here, then notice this is A, that's B, so this would be the ellipticity angle theta. Okay, and because the ellipticity has to be plus or minus 1 or in between, then that means that the angle can only go between minus pi over 4 and pi over 4. So those are the only valid, or that's the valid ellipticity angle range. And following more algebra, we could show, but I'm just going to write it down, we could show that the sine of 2 times the ellipticity angle is equal to 2ax ay over ax squared plus ay squared times sine of delta. So we could get the ellipticity angle directly from the electric field representation values. Okay. And that's really why we have to define ellipticity this way in terms of sine, so that we're consistent with all of this. All right. So, what does that mean? Well, it looks like so far we have 3 ways to represent a polarization state. The field representation, the ellipse representation using the ellipticity, or the ellipse representation using the orientation angle and the ellipticity angle. Yeah.
So what if you're given like the ellipticity or the ellipticity angle, then can you not go back to the field because you don't know what that ratio is?
You can.
Is there some way you keep track of what that ratio is? Because like if you do like your ellipticity is B over A, doesn't that lose like kind of the scaling?
So basically here we have 3 pieces of information. Here we also have 3 pieces of information in that the sine is that 3rd piece of information. So we have orientation angle, ratio, and the sine.
Okay.
And that's enough to get us here. So we can go backwards. And we'll...
you can use the angle then find the magnitudes.
Yeah.
Okay.
Yeah.
Okay.
Yep. Okay. So let's erase this. All right. So let's take a look at the special cases. First of all, linear polarization. And we have that, and let's look at this form right here for EX and EY. And let's say that delta is 0. So So if delta is 0 right there, and I have x is ax cosine omega t minus kz, and y is a y cosine omega t minus kz. Okay, so let's say that we're at z equals 0 and t equals 0. Then where's the electric field on this graph? Pardon? X, Y. So we go out here to AX, then we go up AY, and we're right there. Okay, so in z equals 0, t equals 0, that's where the electric field is, right there. Now let's let the time increase just infinitesimally, just a little bit. And we're still at z equals 0, so we'll just stay at z equals 0. So maybe I'll write that down. Okay, so we let time increase a little bit, then what happens to EX and EY?
Closer to the origin.
Yeah, they get a little smaller proportionally, so closer to the origin. Now I let time increase a little more. Closer to the origin, closer to the origin. In other words, it's going. The electric field is going this way until we get to whatever time pushes us through the origin, and we come out the other side until we get to minus x minus ay, and then time increases. We turn around and we just keep going, and you can see it's just going to trace out that line, right, in time. What if delta was pi? EX is the same, right? And EY is AY cosine omega t minus kz plus pi, which is what? Minus AY sine omega t minus kz. Oh, no, cosine. Pi halves would give the sine. Okay, so at z equals 0, t equals 0, where's the electric field vector at?
Ax and minus a1.
Yeah. Out AX, because that's still the same, but now this is minus AY, so we're right there. So now we let time increase, and this gets a little bit smaller, this gets a little bit less negative, so we basically do this. All right? We good with that? So notice, if delta is 0 or pi, we have linear polarization. Now remember, delta has to be greater than negative pi, less than or equal to pi. So those are our only two choices in that range. Okay, so now for the electric field representation case, we know what the condition is for linear polarization. All we have to do is look at delta. If it's 0 pi, voila, we know it's linear. Okay? Now let's look at circular polarization.
Does it make sense to talk about phi when you talk about linear polarization, like that angle? Is it always just going to be 45 or negative 45? Or
that gets back to what the ellipticity is.
uh,
And here I just happen to draw this so it looks like 45.
okay,
But I could have said, well, AY, maybe it's right
it
there.
can be any angle,
Yeah,
right?
and then it's, then it'd be doing this.
Okay.
Yeah. So that rotation, that depends on the ratio of AY to AX.
Okay.
Yeah. Okay. Then let's let AX be equal to AY, delta, let's let it equal pi halves. So EX would be AX cosine omega t minus KZ, same thing as what we did before. And now EY is AX, because the amplitudes are the same, cosine omega t minus KZ plus pi halves. And then we can use a trig identity, and that gives us minus AX sine omega t minus KZ. So again, let's let Z be equal to 0. And t equals 0, where does the electric field vector start? So it'd be AX
minus AX.
and 0, because sine of 0.
Oh,
So we'd be right here at AX.
Good question. Shouldn't it be AY on the EY? Ah, okay.
Yeah. Good, I'm glad you asked. Okay, now we let time increase just a little bit. What happens to EX? Gets a little smaller. What happens to EY? Gets a little bigger in the negative direction. So it goes over here. And then we let time increase, and basically what happens is we do this. And notice that's clockwise. And delta is greater than 0. Yeah, that's consistent with what we said over there. Yeah. Okay, now if we did, we're not going to take the time to do it, but if we did delta equal minus pi over 2, then we'd just be rotating the other direction. So that would give us counterclockwise circular polarization. So the condition for circular polarization, that is, we have to have AX is equal to AY, and delta is either plus pi halves or minus pi halves. So under those conditions, then we have circular polarization. And only under those conditions. Okay, so we have a few minutes left, so let's do the next thing. And now it gets fun. And unfortunately, we'll have to defer a lot of the fun until next time. Okay, let me define a complex number chi that has nothing to do with electric susceptibility. This is just a complex number. And let me define it as tangent of psi e to the j delta. And let's let tangent of psi be ax over ay. Oh, no, backwards, sorry. Ay over ax. Then I could write chi as ay over ax e to the j delta. Okay, so in other words, if I go back to my xy plane, I go out a distance ax, I go up a distance ay, psi is just that angle, right? Okay, and psi we're going to force to be within the range of 0 to pi halves. Okay, notice this is just a complex number. And we can always go to the complex plane for the real and imaginary axes. And then any point on the complex plane, let's do this, is going to be some distance away from the origin, some angle from the real axis. And notice here the angle from the real axis is just delta. And the distance from the origin is ay over ax, or in other words, tangent of psi. So in other words, every point on the complex plane represents a unique polarization state. So if we were right here, tangent of psi is 0, that only happens if AY is 0. If AY is 0, that is horizontal linear polarization. And as we go out along this, delta is 0, right? Delta 0, that's linear polarization. But this is changing. So basically what's happening is the orientation angle of the linear state is rotating. Until we go off at infinity, the polarization is vertical. Likewise, going the other direction, every point represents more and more rotation clockwise until off at infinity, we're vertical again. If we go in this direction, then delta is equal to pi halves, right? Pi halves. So as we go up, this is going to be a squished ellipse. Delta is greater than 0 up here. That corresponds to clockwise. Once we get up here to J, then AX is equal to AY. That's clockwise circularly polarized light. We keep going, start squishing down in that direction. We go off to infinity. We're back to linear vertical polarization. Same thing in the other direction. Same thing in the other direction here. Now we're just at some rotated ellipse. And up here, delta is greater than 0, so we have clockwise rotation. Here, delta is less than 0. We have counterclockwise rotation. Bottom line is, every point on the complex plane represents a unique polarization state. Therefore, we could have a complex number representation for polarization states. And we can specify either the complex number. We could also instead specify psi and delta. We could change delta to be a capital delta, just because. And the capital delta with psi, those are called the ellipsometric angles. And that's the ellipsometric angle representation of polarization state. Okay, so how many representations do we have now? 4. 1, 2, 3, 4, 5. And we're just getting started.
So why is there a representation that's more common than the rest, or one that
It
people
really
default to?
depends on the field.
Okay.
And so that's why we're just going to learn them all, or most of them, because they're not that hard in the first place. And then when we know how to go between them, it doesn't matter which one gets thrown at us. We can go to whatever we want to, whatever we're happy with. Okay, so we're kind of in the middle of it. We'll pick up here on Thursday and learn some more polarization representations, and then start figuring out fun things we can do with polarization. All right. Well, enjoy. We will see you Thursday.